Zero trust is best understood as a change in assumptions because it rejects the idea that being on the inside automatically makes activity trustworthy. Traditional network thinking often treated the internal network as a broadly trusted zone, then focused security effort on the perimeter, hoping that anyone who got past the edge was mostly legitimate. That model breaks down in modern environments where cloud services, remote work, third-party access, and compromised endpoints are normal realities rather than exceptional events. Zero trust changes the baseline expectation by removing implicit trust based on network location and by insisting that access must be earned repeatedly, not granted once and forgotten. The practical outcome is that connectivity becomes more conditional, more explicit, and more tied to identity and context than to a particular address range. Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A central principle is that every request should be treated as untrusted until it is verified, even if it originates from a device that appears to be on a corporate network. Verification is not a single step. It is a series of checks that confirm who the requester is, what they are trying to access, and whether the request aligns with policy at that moment. This mindset is valuable because attackers frequently obtain internal footholds through phishing, credential theft, or compromised partners, and once inside, they rely on implicit trust to move laterally. If you force verification for each meaningful access decision, the attacker must repeatedly overcome controls rather than benefiting from a one-time breach. That repeated friction is not about making systems hard to use. It is about making unauthorized access hard to sustain. The core ideas that support this approach are strong identity, least privilege, and continuous evaluation, and it is important to treat them as a connected system rather than independent slogans. Strong identity means you are confident in who a user is and what device or service is acting, which requires robust authentication, trustworthy identity stores, and careful lifecycle management. Least privilege means access is scoped so that users and services can reach only what they need, reducing the blast radius of compromised credentials or misused permissions. Continuous evaluation means access decisions are not static. They can change when risk changes, such as when a device becomes unmanaged, a credential shows suspicious use, or the sensitivity of the requested resource demands stronger proof. When these ideas reinforce each other, the network and applications stop granting broad-standing access and instead grant narrowly defined, context-aware permissions. Policy decisions in a zero-trust model consider user, device, location, and sensitivity context because the same action can be acceptable in one context and dangerous in another. The user context includes role, group membership, and recent authentication strength because a privileged administrator accessing a control system is different from a general user accessing email. The device context includes whether the device is managed, patched, and configured according to organizational standards, because compromised or unmanaged devices should not be treated as equivalent to healthy endpoints. Location context can include network type and geography, not to create blind trust, but to add signals that influence risk, such as whether the request originates from a known corporate site or an unfamiliar region. Sensitivity context is about the resource itself, ensuring that higher-value systems require stronger assurance and tighter access scope. Microsegmentation is one of the most tangible ways to implement zero trust because it narrows the allowed pathways within networks and reduces the default ability for systems to communicate laterally. Instead of broad segments where many hosts can talk freely, microsegmentation creates smaller zones and more specific rules that define which workloads, users, or services can communicate. This is not merely network hygiene, it is a direct countermeasure to lateral movement, because attackers often pivot from one compromised system to another by exploiting permissive internal connectivity. With microsegmentation, a compromise in one zone does not automatically grant reachability into adjacent systems, and policy can be written to reflect real business relationships rather than network convenience. When done well, microsegmentation makes the network's communication patterns more intentional, which improves both security and monitoring clarity. Software-defined networking changes how networks are controlled by separating control plane logic from data plane forwarding, and that separation is the conceptual bridge between network architecture and zero-trust policy enforcement. The data plane is responsible for moving packets based on forwarding rules, while the control plane is responsible for deciding what those rules should be and distributing them. In traditional networks, much of that control logic is distributed across devices, each making its own decisions based on shared protocols and local configuration. Software-defined networking centralizes or logically centralizes decision-making so that policy and intent can be expressed in a controller, then pushed to the forwarding devices. This separation enables more consistent policy enforcement and makes networks more programmable, which is why it shows up in discussions of adaptive segmentation and identity-based control. Centralized controllers in software-defined networking program network behavior dynamically through policy, which means you can express intent in higher-level terms and have the controller translate that intent into concrete forwarding and filtering rules. Instead of configuring each switch or router independently, you use a controller to distribute consistent rules across the environment, reducing drift and improving repeatability. The controller can also respond to changes, such as adding a new workload, moving a service, or adjusting segmentation based on updated policy requirements. This dynamic programming capability is especially valuable in environments where infrastructure changes frequently, such as in cloud or large virtualized data centers, because manual per-device configuration cannot keep pace reliably. The important security implication is that the controller becomes a key governance point and a high-value asset, since it can shape connectivity across the network. One of the strongest operational advantages of software-defined networking is that it enables rapid segmentation changes and consistent rule deployment, which is exactly what zero-trust architectures often require. When policies evolve, or when an incident demands containment, you want to be able to adjust pathways quickly and apply the change uniformly, not device by device with uncertain completeness. Consistency matters because a single overlooked segment or a single misconfigured switch can become the path an attacker uses to bypass your intended controls. With software-defined networking, you can express segmentation and access policies once and have them applied broadly, which improves both speed and correctness. This does not eliminate the need for careful testing and change control, but it changes the mechanics so that policy becomes centrally managed rather than manually distributed. In a mature environment, that improves both security posture and operational agility. Identity-aware controls are what connect zero-trust principles to network behavior because they link access decisions to authentication and authorization systems rather than to static address-based assumptions. Instead of saying, anything on this subnet may reach that server, an identity-aware approach aims to say, this authenticated user or service under these conditions may reach this application. To do that, network enforcement points must integrate with identity providers, policy engines, and authorization data so they can map traffic to identity context. That mapping can be straightforward in some application layer gateways and more complex in pure network layer enforcement, but the direction is the same. Identity becomes the anchor for trust decisions. When identity-aware controls are deployed correctly, the network reinforces the same access rules that applications and identity systems define, which reduces gaps and reduces reliance on network location as a proxy for trust. Device posture checks are another crucial signal because they validate managed state before granting sensitive access, and they help prevent compromised or unmanaged devices from becoming trusted conduits. Posture checks can evaluate whether a device is enrolled, whether it meets patch and configuration requirements, and whether it shows signs of compromise or risky software. The key point is that identity alone is not sufficient because an attacker can steal credentials, but it is harder to convincingly imitate a healthy managed device while also sustaining malicious activity. By requiring device posture compliance for access to sensitive systems, you reduce the chance that a compromised personal device or an unpatched endpoint can directly reach high-value resources. This is also where operational discipline shows up, because posture checks must be accurate and fair, avoiding brittle rules that break productivity while still enforcing real standards. When posture is part of access decisions, the system measures trust based on multiple signals, not just a password. Telemetry is what enables continuous access decisions and risk-based adjustments because it provides the ongoing signals needed to decide whether access should remain in place, be limited, or be revoked. Telemetry includes authentication events, network flow patterns, endpoint health signals, and threat detections that indicate elevated risk. When telemetry is integrated into policy, access can become adaptive, tightening controls when suspicious behavior is detected and relaxing them when conditions are normal, within the boundaries defined by governance. This is not about constantly interrupting users, but about making the system responsive to changing risk in a way that reduces attacker dwell time. It also improves incident response, because containment can be expressed as policy adjustments rather than improvised firewall changes that are hard to track. Telemetry turns zero trust from a static access model into a living control system. The deeper philosophical shift is that trust is measured through signals rather than network location alone, which aligns with how modern environments actually function. Location can still be a useful input, but it is not a decisive credential, because internal networks can be compromised and external networks can be used by legitimate users. Signals such as authentication strength, device health, user behavior patterns, and resource sensitivity provide a richer basis for deciding what should be allowed. This signal-based approach also supports more precise least privilege because you can grant access to a narrow resource under strict conditions rather than granting broad access based on being inside a boundary. The result is a system that is more explicit about why access is allowed, which improves auditability and reduces accidental overexposure. When signals drive trust, the architecture becomes more resilient to the reality of distributed work and hybrid infrastructure. Governance is what prevents zero trust and software-defined networking from devolving into ad hoc rulemaking because it defines policies, exceptions, and accountability for access decisions. Policies must be clear about who can access what, under what conditions, and with what levels of assurance, and they must be maintained as systems and business needs evolve. Exceptions will exist, but governance ensures they are justified, time-bounded when appropriate, and visible so they do not become permanent hidden vulnerabilities. Accountability matters because when policy is centralized and dynamic, changes can have wide impact, so you need defined ownership, review processes, and evidence of why decisions were made. Governance also sets the expectations for logging and auditing, ensuring that access decisions can be traced back to identity and policy at the time they occurred. Without governance, the technical capabilities of software-defined networking and zero trust become risk multipliers instead of risk reducers. When these ideas come together, zero trust and software-defined networking enable adaptive, identity-centered network control that matches modern threat realities and operational needs. Zero trust removes implicit trust and insists on verification for each request, while strong identity, least privilege, and continuous evaluation provide the structure needed to make that verification meaningful. Policy that considers user, device, location, and sensitivity context creates decisions that reflect real risk rather than simplistic boundaries. And microsegmentation narrows pathways so lateral movement becomes harder. Software-defined networking provides a programmable foundation by separating control plane logic from data plane forwarding and allowing centralized controllers to deploy consistent rules quickly across changing infrastructure. Identity-aware controls, device posture checks, and telemetry-driven adjustments turn access into a responsive system rather than a one-time event, and signal-based trust keeps decisions grounded in evidence rather than assumption. With governance defining policy, exceptions, and accountability, the result is a network and access model that can change safely, enforce consistently, and defend itself under pressure. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.